Our next speaker is Jeff Valenti, and from the interior of the stars, we are now going to the atmospheres and spectroscopy. So Jeff is going to talk to us about things like opacities.
Exciting things like opacity.
Very exciting and very difficult things like opacities.
I'll understand if you guys are doing those tutorials that Jesse just pointed out. Those looked good. I really want to do those, but I have to give a talk now. So yeah, my collaborator in this is Nikolai Piskunov. We have together been producing tools to support the community doing spectroscopy. I'm going to report on some work we've been doing on continuous opacities in the ultraviolet. So why do you care about opacities? Well, one thing is you or your friends may be trying to do broadband colors, stellar populations, something like that, and relying on models to make those predictions. Perhaps you or your friends are trying to do abundance measurements where the continuous opacities are very important. They affect the level of the continuum and hence the equivalent widths of the lines. Or maybe you or your friends are trying to do exoplanet atmospheres, and you know that there's photochemistry that's driven by the near ultraviolet flux, the ultraviolet flux, and so they come to you and they say, hey, is this model of the star right? And you have to have an answer for them. I'll let you guess what it is. Okay, so one of the first points I want to make is that high-resolution flux-calibrated spectra can reveal continuous opacity errors. As every good parent does, I'm going to say, don't make the mistakes I made as a youth. I have a long career in high-resolution spectroscopy, and I pretty much always normalize the continuum to 1, and therefore don't detect errors until much later downstream. If you can, get flux-calibrated spectra. So this little equation, it's the equation for my talk. On the right-hand side, you have whatever comes out of a radiative transfer code. For the talk, I'll be showing mainly results from Spectroscopy Made Easy, which is the tool that Nikolai and I provide to the community. There's a very difficult way to convert that into what you would actually observe. You multiply by that angular radius, right? If you went to the Chara talk, you know that we have 300 or so stars with angular radii measured to better than 5%, in some cases better than 1%, as in the examples I'll show here. And then, of course, with astroseismology and Gaia or whatever, you have other ways that you can get that same quantity to high precision. Then you have your observed spectrum. In the case of HST, which is what I'm going to use for an example here, the flux calibration is quite excellent. I'm hoping that you all will do a better job than I did getting flux calibrated spectra from the ground at high resolution. And let's see what you can get. So this is in black, an HST high resolution spectrum of alpha Cen A, so perfectly appropriate for this conference. I've degraded the resolution to only 300 just to show you the challenges of trying to understand what's going wrong at low resolution. The red is a model, in this case generated by SME, that's available on my website today. It was put there back in 2016. So people are definitely using this code now. And I've degraded the resolution of that to 300 as well. And you can see that there are errors. This is a logarithmic plot, so there's factor of 2 errors on the left-hand edge, a little bit smaller on the right-hand edge, and middling success in the middle. But it's really hard to tell whether this is missing line data, which is what I grew up thinking, that there's just a bunch of lines in the ultraviolet, and that's the problem. Is it that the atmosphere is not right because something's going on? Or hypothetically, could it be continuous opacity problems? Who knows, right? So this is now the same observed spectrum in the same model, but at a resolution of 100,000. And of course, I can't show you the whole thing as much as I would like to. So this is the left-hand edge where the error was very large at 2,000 angstroms. Again, the observation is in black, the model is in red, and you can see there's factors of a few error in the model. And the errors I've highlighted in the dashed lines where the peaks of the discrepancy are largest, and you see that they map down to areas where there really aren't very many spectral lines. It's just where the observed continuum is pretty flat. This is the right-hand edge of what I was showing you before in low resolution, right? So this is and it's a regime getting closer to the optical where we have lots of data. And this time I'm highlighting with the vertical dashed lines that the line cores, the cores of the strong lines, they're actually pretty well described by the model, right? The red curve goes through the black curve. There are some discrepancies in places, which is certainly errors in the line data, but the line data is pretty good. The line data come from VALD3, the Vienna Atomic Line Database. This is a wonderful service to humanity that provides curated line data tailored to whatever temperature star you're interested in modeling. So how can the line cores be good and between the lines not? Well, what's happening at any point in this spectrum is the brightness of the spectrum, of the model spectrum, depends on what the total opacity is. In the line core, you're dominated by the line opacity, and any errors in the continuum opacity are irrelevant. They're a tiny fraction, negligible fraction of the opacity. But between the strong lines, now you are dependent on the continuum opacity. So this is the signature of an error in the continuous opacities in the ultraviolet. And so this leads me to my conclusion. We need more continuous opacity in the NUV. It's an empirical result based on what I just showed you. So that's point number one I want to get across to you guys. All right, so what is under the hood in SME on my website right now? So the dominant source of continuous opacity in the visible and the infrared, which is the right 2/3 of the diagram, is H-, which we all learned. That's what I learned, right? And that's good news because that's all pretty much right now, still right. When you get to the ultraviolet, what we have is photoionization of neutral metals, carbon, et cetera. And that's the blue curve, it's, superposition of various edges, atoms in some state being photoionized. Okay? What I learned when I tried to track down what was going on, I saw this paper by Juan Fontenla, which showed that for the sun, actually photodissociation of molecules is more important in the ultraviolet than those photoionization edges I was just showing you. And the three molecules that he's tracked down and used in his code are CH, NH, and OH. This plot shows the cross-section of those opacity sources as a function of wavelength. You can see around 2,000 angstroms, CH has got a big peak, and so that's what was causing the problem in the first high-resolution spectrum I showed you. And near 3,000, there's a little bump by NH, which I will show you is not enough to explain the problem that I'm seeing at 3,000 angstroms. From that same paper, this is solar observations in blue and red. And then there's two models here. There's one in black, which is the model that includes the photodissociation from those three molecules I just showed you. And it does a pretty good job of modeling the sun. And then there's one in purple where he just turned off that opacity. And you can see that it's really bad around 200 nanometers, 2,000 angstroms. And then near 3,000, it's not clear exactly whether it makes a big difference, this opacity. Jolene Karlberg gave me this beautiful figure yesterday. She's looking for beryllium. This is the use case number 2 from my motivation. You want to measure abundances. In this case, beryllium, which you have to go to these wavelengths to measure. There's a lot of other stuff, line opacity in this region, so it's not easy. There's two curves here, a dashed curve, which has CH and NH photodissociation, and a solid curve that doesn't. And the reason I'm showing you this plot is because the top is a dwarf, which is like the case that I'm showing you with alpha Sen. And when you go to and it doesn't actually make a big difference in this wavelength range, but when you go to giants, not surprisingly, it does make a difference. All right. So second point I want to make, molecular photodissociation is an important source of continuous opacity in the ultraviolet. So I just want to say when I wanted to go implement this in SME, as I often do, dug deeper into literature, and I saw that 20 years ago, Babka Roots had already figured out half of this, and that's sort of the story of my career and maybe many of the rest of us. So thanks to him. So we stole his routines for OH and CH. Philip Stansel had just calculated NH, which is where Fontenla got them from, updated some photoionizations from Bautista and other atoms from Roots. Magnesium needed to be updated. Here's the same high-resolution plot I showed you before, the red and the black, but now the blue, once you put in the the CH photodissociation, which is the key here. It's a typo on the slide. Substantial improvement. Not perfect, but definitely we made progress. Here's what's going on in the other high-resolution section I showed you. The red and the blue are almost indistinguishable. It was really minimal improvement. There's still a big discrepancy between the model and the observation, so that leads me to my... Oh, and there's a similar issue if you were to look, for example, at the beautiful spectral library Husserl provided everybody with the Phoenix models. So that leads me to my third and final conclusion, which is we are still missing continuous opacity sources in the ultraviolet. And when your friends say, why can't I explain my data properly, just remember that it could be this if they're looking in the blue. For posterity, when I put it online, all the acknowledgements of the contributions from the people that calculate the atomic data and make things available to the community. And then just to repeat the three conclusions, high-resolution flux-calibrated spectra are powerful. Molecular photodissociation is an important continuous opacity source, and we're missing some opacity still. Thanks.
Thank you, Jeff. And there's a question there behind you.
Sasha Shapiro, Max Planck Institute for Solar System Research. So my question is, why do you think that it is actually continuous opacity which is missing? Yeah, because what people routinely do, at least in solar physics, they fudge the continuum opacity. Yeah, so they found the ratio by which you have to multiply your continuum opacity to reproduce the spectrum. And this ratio looks really crazy. Yeah, so there is no good dependence on the wavelengths, which would probably say that what we really miss, it's a huge amount of unresolved atomic or molecular lines, yeah, not necessarily continuum opacity.
Right. So I can't excuse me. I can't completely rule out a sea of weak lines, but and that may be the case in some regions. But the line lists for molecules are getting better and better. The craziness you see could be due to line opacity in certain regions that is not right. The continuum that we observed in the 2000 region is flat. So I'm leaning strongly towards continuous opacity, but I cannot rule out completely a sea of weak lines.
Okay. Thank you for doing this very important work. The problem of missing opacity goes back to when I was a graduate student, which is a long, long time ago. And I just want to comment.
With a question.
Here's the important part. Juan Fontenla has fit reasonably well the solar spectrum with CN, CH, OH, and wanted to go further. And the last time I talked to him, which is just before he passed away in January, he said two things. One is he's looking carefully into helium, some forbidden transitions in helium. And secondly, he said it's very important to get the UV emissions shining down and photodissociating those molecules in order to get the opacity right. So that's, I think, the two areas that may well explain the missing opacity that is still there.
Thank you.
Rainer?
Rainer Tramberg, Space Science Institute. Thank you very much for pointing this out.
You're welcome.
I couldn't quite read your whole list of, so Sultana and Anil mentioned there. Sultana also curates a database, NORAD.
Exactly.
Is that where you've taken your bound-free opacities?
No, actually. I mean, some of them historically come from there. For magnesium, I took from there, but otherwise, no.
Okay, we should maybe talk.
Sure, thank you.
There was a question at the back. There, yes.
Ulrike.
Hi, Ulrike Heiter from Uppsala University. I was wondering if you could fix these continuous opacities and find all the sources, what kind of effects would you expect for other regions of the spectrum, the optical, for example? Or
yeah, so I actually I don't have much experience calculating the atmospheres, but I agree with the implication of your question that if you block the flux in the ultraviolet, there needs to be some sort of adjustment in the rest of the atmosphere to get the flux out at other wavelengths. And so the colors would change, the spectrum would change a little there as well. So I agree with that.
And one last question, Mark.
So, Jeff, I perhaps have a naive question, but when you do these models, you're assuming a uniform atmosphere, but the UV is particularly sensitive to the inhomogeneities in the solar atmosphere, and I was wondering if that has any impact,
Right.
what your thoughts are on that.
It may indeed have an impact. The sign of that effect is opposite from what we're seeing, right? I mean, so if there's activity, you would normally expect the continuum to be brighter, and we've already got it observed to be, I mean, the model is too bright, and so if we put activity into these models, I would guess that they would get even brighter still. So if we want to use the continuum to study activity, we have to fix this problem first, and then we can start using the continuum to try to diagnose what the heating might be in the upper atmosphere.
Thank you very much, Jeff.
Yeah, thanks to you all for the questions.